Hi, everybody. I'm Matteo. I'm a third year PhD student in the space propulsion group, and I'm working under the supervision of Eduardo and Mario. And my thesis is titled Stability Analysis of Magnetized Plasma Flows for Space Propulsion. The focus of my research is instabilities in magnetic nozzles. And what are magnetic nozzles? Now, we've been talking about mature technologies in space propulsion, electrodeless plasma thrusters and magnetic nozzles a little bit less. But anyway, so they are the accelerating device of electrodeless plasma thrusters. And so they function as a nozzle. So a plasma converts thermal unorganized energy into organized kinetic energy and accelerates. They function as partially magnetized E cross B plasmas, partially magnetized because the electrons, as you saw in the funny animation before, they follow closely the magnetic field lines, so they're fully magnetized. We consider them like this. Instead, ions, they are much more, they're much heavier, so they stick more to they don't really feel the effect of the magnetic field, very little, so they stick more to inertial trajectories. And they're E cross B because the electric field and the magnetic field, they're not parallel one to each other. So now these thrusters here, they are, as any other thruster, any other device, they are subject to cross transport. Some of these is due to trivial sources, for example, collisions. We know that they make electrons cross magnetic field lines. But then there is a part of this which is not really well understood, that is not captured by classical models. We call this anomalous transport. And since we know experimentally that there are fluctuations in magnetic nozzles, we think that instabilities and time-dependent phenomena, they might play a role in making the electrons cross. So this is where my research comes in. So we study instabilities. First, we study the physical criteria, the physical mechanisms that trigger them. Then we study their effect on cross-field transport of species and how they impact performance. And then in the end, from this, we would like to get as an output something to maybe make our models better, more predictive, and more self-consistent without using phenomenological parameters like, I don't know, anomalous collisionality. Okay, so there are multiple approaches to study instabilities, and this depends on which set of equations you consider. For example, you can study the problem from a kinetic approach, and then you study the perturbation of loss of equations. So you study directly how the distribution function gets affected by time-dependent, like by a perturbation. And then you end up studying, for example, particle wave phenomena and resonances between the two. Borja can help you with that. Or instead, if you consider the fluid equations of the plasma, and you consider how these can evolve in time, then you're using a fluid approach. And these ones are more relaxed mathematically, but you need some closure. You need to be careful on that. Then other things that characterizes the instability analysis. There are local approaches where you consider your wave to be short enough in wavelength to not be affected by boundary conditions of your problem. So you are assuming the eigenfunction of your problem. Or you might want to study how boundary conditions affect your problem. And this is the global approach instead. Then you might consider your perturbations to be small, so you can linearize your equations that you're considering, so linear approach. Or you take entirely all the nonlinear problems and you brute force the equations. This is the nonlinear approach. The first step of my thesis was fluid local linear analysis of waves in a magnetic nozzle. So as I said before, this reduced the complexity of the problem to a degree. But this confined us to study long wavelengths because we didn't want to sample, for example, particles in their gyro orbits, and to very large parallel phase velocities to avoid particle wave resonances like lambda lumping. And from the entire model, we got a dispersion relation which relates the frequency of the wave you're considering to its wavelength. And we applied it point by point to data from simulations from Pedro of a magnetic nozzle. We use this as kind of equilibrium data. And then we applied it and we looked for the most unstable modes here. So what we found, this is already presented last year, so I'm gonna go quick. We found frequencies of these most unstable modes which fall in the range of experimentally observed fluctuations. And the most unstable waves were predicted by our model to be mainly azimuthal. Then we took this data and we tried to see how these instabilities affect the equilibrium values through quasi-linear analysis. And what we found was mainly an outward electron flux. So what it means is that the plasma is kind of pushing itself against the gradients, which they're the same, they're the very reason for which the plasma is unstable. So it's kind of trying to flatten out its energy sources. Then we did half a step in a more difficult direction with a collaboration with Jesus Ramos. And this is, so we switched to kinetic local linear analysis, but we restrained ourselves to, equations, to perpendicularly propagating waves. Here, what we consider were ions as a cold fluid, cold and magnetized fluid, while electrons were described through the drift kinetic equation, drift kinetic version of Vlasov equation. So as you can see, that form here. And we found out that the equilibrium mainly, the stability thresholds mainly depended on 3 parameters, alpha, beta, and delta, which by themselves, they depend on the gradients of magnetic field, density, temperature gradients, which is the main novelty, by the way, and the potential, electric potential. As you can see here, the marginal stability curves are much more difficult to understand with respect to the fluid ones. For example, the blue, very quickly, the blue lines are lines where conjugate complex roots meet on the real axis, so they pass from being one unstable and one damped wave, they become 2 stable waves. Instead, the green and red lines are lines of resonance, so the particles are resonantly interacting with the drift waves present in the plasma. Okay? This is a side hustle. This is not really, I had to put this on hold because I wanted to evolve a little bit the local fluid linear analysis. And here I was looking for eigenfunction still of waves in a magnetic nozzle, but still, this is a project that I will continue maybe in the future. Nothing, it is just pretty plots to show you, for example, the modes. Here I solved analytically for the plasma column in a simple case. In a magnetic nozzle, the situation is going to be a little bit more chaotic. Now, the real step forward is the now passage from theory to numerical. And now I'm wanting to approach the entire problem of waves in a magnetic nozzle from a kinetic global nonlinear point of view. So kinetic global nonlinear, this is, for example, the application case of particle in cell codes. So what I did was I took the 2D code developed by Alberto and Enrique Picasso. And the thing is, as we said before, from the previous study, we saw that mainly stabilities were azimuthal, so we might want to add a third direction to the study of the magnetic nozzle, waves in the magnetic nozzle. Okay, so how do you do this? You can do it 2 ways. So first, like Picasso, what he has is like it discretizes the space in a 2D grid because you consider meridional cuts of your problem, okay? So if you want to make it 3D, you might want to extend this grid to the third direction, and so taking a number of discretized angles to see how the problem evolves in that direction. Sorry. Instead, what you can also do is you take the macroscopic properties, for example, electric potential or densities of your plasma species, and you decompose them into an arbitrary number of periodic modes, okay? So like a Fourier decomposition, very simply. Then you use the orthogonality of this to then solve the Poisson equation for each mode independently. So first you deconstruct, you solve, and then you reconstruct the mode, you get the fields, and then you advance in time the movement of you push in time the particles. Okay, so what you say, what do we do? We choose a discretized number of modes that we want to solve our problem for, and then we reconstruct. So there is still a sort of choice, there is still a sort of grid, but it's like a spectral grid more than a physical one. So the model, the code now started from a zeta R configuration, and what we did, for example, here, this is a very simple case just for show of a plasma column. What I wanted to show you is that, for example, in this case, now there is a third direction. Here I took a cut at a constant radius, and as you can see now the problem takes into account, in this case, only plus minus 1 mode, but you can extend it to plus minus 10 up until the point. So now the code is moving into a 3D direction. Okay, so my achievements, more or less, what I did was, we have a paper under review in Physics of Plasmas on the first work on the magnetic nozzle. We're going to send soon the work with Jesus Ramos of kinetic effects of drift-gated modes. Last year I went to YPC as Simone and the others. Then with Simone we did Semana della Ciencia, but most importantly, I participated in the Liga Interna de Football de Sala with the team of the aerospace department. There is a detail, they only won when I wasn't there, but details. So thank you very much for listening to me if you have any questions.